Alright, time for another debatephysics.com, also video presentation. I guess I'm so tired of this crap. Anyway, so I'm going to go over a couple of experiments and just this whole argument about how there are all these little subtleties and variables in experiments, and you have to account for them. They're not irrelevant. They're really important. And, science should be about really credible, good experiments, not weak, silly, deceptive experiments, frankly. Like dropping round objects, denting clay, just denting the surface with round objects. Not good science. And a couple hundred years ago, you could get away with it and fool everybody. You shouldn't be able to get away with it now. And apparently you can, though. Lots of not very credible science going on. And, more than I have to be concerned. It's not going to, there's it's just a little point. If you're going to behave like flat earthers, then that's what your science is going to be, is silly Sasquatchian bullshit. It's fable science. So anyway, this is an interesting demonstration of this problem of variables and how, frankly, you get a pretty good indication that something's amiss, and you have to figure out why the experiment isn't doing exactly what you would have expected, no matter what you believe. Anyway, so I'll play a little of this, hopefully, if I can find it. Hello, where are you? I have to go find it. I have to find the play button. Alright, I believe we're good to go.
Reaction platform here with a
So action-reaction platform. So the idea is you have something and you're going to do that thing where, you could just launch a rubber band on a surface and then go nowhere. Or you can launch something off your surface and then you get the equal and opposite Newtonian reaction. So that's basically what this is a demonstration of. And so simple enough, right? I mean, I guess I could use my arrow. Got a rubber band stretched, a string of known length, and then a match and a rubber band. So you're going to burn the rubber band, the string, and then the rubber band, blah, and they're going to shoot a ball. Now, there's no real pocket for the ball, so that's a little bit arbitrary and sloppy, but whatever. So you're going to try first with a very light wooden ball and then with a very heavy ball. And it's sort of going to illustrate what I've been trying to explain, that these springs and rubber bands, you have to kind of think ahead, okay, because they do leave energy behind if you don't account for it. So, we've mentioned before the lever launcher, so I guess I'll be talking about that later, and that's a really good way, using a lever, to eliminate this problem by creating the same motion in the rubber band, so you don't have to worry about the fact that something's lighter, the rubber band's moving faster, and it's going to leave more energy stuck in the rubber band kind of idea. But this demonstrates it pretty clearly. Now, I did have a video I made where I put the two clips together and I lost it. So unfortunately, you're going to have to look at it and then remember what that looked like, and then you'll see the next version and you have to remember what that looked like.
That's rubber band held back with a string, and we're going to burn that string with by lighting the match. We're going to put the ball in here, and then we're going to do the same thing again and shoot it again, but this time with a metal ball. And so the question is, which one will have more recoil, with the wooden ball or with the metal ball?
Now, you would say logically that, well, it's supposed to be an equal and opposite division of the energy, so in both cases the ball should get its half and the platform should get its half. But it doesn't happen, in the sense that this is the problem that they don't account for, is the fact that when you shoot the lighter one, there's still energy in the rubber band that you didn't use. And the heavier one, the rubber band moves much slower, so when it's done pushing, you can understand the rubber band is now moving much slower, so it's going to have less energy left in it. And so that is the huge difference, and it's a huge difference. You wouldn't expect it to matter this much, but when you see it, you'll see how dramatic the difference is. And you're saying, well, if I was measuring the energy of the rubber band, one experiment tells me the rubber band has 1,000 joules, and the next experiment says it has 3,000. It's that dramatic a difference.
So let's load this up, and
unfortunately, it doesn't tell us the weights or any of that crap, blah, 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 blah.
See what happens.
So there'll be a slow motion part, so that'll be the part to watch. Yes, I should have found the cut video. So you see not much wobble, but some wobble. Alright, here's the slow motion. So just watch how far it moves. You got that nice little gray pole there, right? So you can just watch by how far it goes past this gray pole. And that'll tell you something about how much motion the platform got. Right up to the edge of it. That's as far as it got. Right past it. And then it goes and it just oscillates back and forth. And you shall see soon, okay, that the heavy ball is dramatically different. There it goes. Dramatically different. Okay, it's just, you know, it's not a, it's at least a two-fold difference, perhaps much more. So we'll play this. So watch the slow motion. Watch how much further past the platform, past that gray rod, the platform goes. So it's way off the screen. So the other one, okay, the front of the board barely got past this pole. So the front of the board went from here to here. And in this case, it went from here to off the screen. So a gigantic difference. And so I'm just saying, realistically, do you think the rubber band has more energy in one case than in the other case? Or is the sensible conclusion that the rubber band can't push light things as efficiently? It's just a fact. It can't dispose of its energy into the object, because frankly, to push it fast means it has to go fast. And when the light thing is going fast and leaving the rubber band's still going very fast. It still has a lot of energy left when it disconnects from the ball. And so now it's just stuck doing the back and forth thing and creating no forward progress anymore. So it can't launch the wooden ball at anything like the commensurate momentum to the momentum it can give the heavier ball, because the rubber band's all moving much slower. It has less momentum stuck in it, and it gives away all of its energy instead of just a portion of its energy. But just watch how much swing you got here. We'll let it come back off. It's way off screen. So much more motion.
Nice. Well, so
okay, so they have no, you know, they just say, oh, look here, so I've got a bunch of math here to try to figure this out, but just it is a little bit weird. So they don't say anything about the experiment and what it actually demonstrates, which is just kind of irritating. Because, again, what are your possible options? To say that the rubber band itself, stretched exactly the same, released exactly the same, somehow apportioned two different kinds of energy. In one case, the total amount of momentum going both ways, 3,000. In the other case, 1,000. That doesn't seem plausible at all. That's like saying, you know, any explosion, any amount of gunpowder, I can make the gunpowder have more explosive power. And I really can't. You have to add it all up. There's exhaust, there's this, there's that. You know, if you add it all up, it's got to be conserved. And quite frankly, the momentum is not being conserved in this case. And I think the obvious conclusion is it's a problem with how the experiment is being done. All right, so that probably is enough. I mean, that was dramatic enough. I don't need to show it again because I think you can concede. Yeah, that was pretty dramatic. All right, so then we have this thing. All right, so me and Paul Nord are still discussing experiments. So he 3D printed this thing, which is really quite, I believe it's 3D. I mean, it looks, has every indication he 3D printed it anyway. So basically it's a puck that would be on an air hockey kind of table, and therefore we could put it next to a surface here, and this little plunger would be extended. Then it would be released, and it would push against the surface and launch the puck. And then you could put weights in these little holes and say double the weight and see if momentum is conserved or kinetic energy is conserved. Now, the big problem is there's little stops right here. So again, you have the same kind of argument can be made. What is the likelihood of what's going to be the momentum of this piston in the two circumstances? So when this thing is light and will move away, okay, at a higher velocity, twice the velocity presumably, obviously the little plunger is going to be moving twice as fast relative to the body. That is, this plunger will move away from the body of this puck at twice the speed when it's half the mass. And so obviously when it hits these little stops, right, so I don't know if you can see these are little stops here. So the plunger goes back and then it hits the stops. So obviously that would be just like a piston on a gun, and I fire the piston and there's a stop, so the piston stops, and that's going to mean that all of the momentum I got that way gets ruined by momentum this way and I get no motion. So obviously that would tell the puck it shouldn't move because it's getting hit in the opposite direction, right? I mean, the puck can't go that way if the piston just hit it that way. Now the problem is if you release that is you just cut those little stops off and let the little thing shoot out. Well, that seems fair in the sense that, okay, you're going to shoot it out at the same speed in both experiments, right? But again, you're not, because of the relative motion, right? So if this puck has weights in it, it means the puck is going to move slower away, which means relative to the rubber band, it's still going to be slower. So yes, the piston will leave at the same speed, but the motion of the object and the rubber band's motion is going to be different because the whole puck will be moving twice as fast in one circumstance. And so the puck is doing the motion, okay, that's going to be twice as much as it would be with the weights. And so obviously, even though the piston leaves with the same velocity, the puck is not going to be absorbing the same amount of energy, because in one case the rubber band is going to be moving a different speed than in the other case. And so it's a little hard to figure out a way to do this experiment fairly. I mean, in a way that's going to give you any kind of reasonable answer. So the problem is that, yeah, we can say, hey, how much can it matter? The piston can't weigh that much, this can't weigh. And apparently it does matter, as it just showed in the previous experiment where you had this dramatic increase. So the more mass you had on the rubber band, the more energy you got out of the experiment, and the less mass, total mass you have, the less energy, the less total energy you collect. So, you know, it's just a fact, okay? And I mean by energy, momentum. And, you know, if you believe in conservation of momentum, you've got to, you know, concede something's wrong there, because I can't destroy momentum. It's got to be somewhere. So I have to explain where the hell is it. And the only explanation for where it is in the rubber band. The rubber band never released all of its energy. All right, its full capacity was not realized, however to say that. All right, so that might be enough on that. And so then I can go to the example of the lever. Yeah, and then I might change the subject to a little bit about the Veritasium garbage video too. All right, so what I need now is this. And draw. Okay, pen. Oh, I have to find that. Yeah, back. So, now this was first developed by the Brozo. Not a very reputable character, but it's a perfectly sensible way of overcoming this limitation. I don't think he really understood the principle much, but regardless. So, this is my modification to the idea. So you just have a regular lever, make yourself a good little fulcrum, nice solid secure mounting, and the idea is you take a rubber band or a spring, all right, and you're going to use that rubber band, you're going to give it a certain compression, okay, so you're going to push the lever up this way and expand it, and then you're going to tie the lever down, okay, with another little string over here, so you have a nice little quick release. So this is a standard size string, and you're just going to cut that, okay, to facilitate a quick release. All right, so the idea is now you can create a system where you can launch a 2 mass and a 1 mass at locations consistent with the law of the lever. Okay, now they'll have to be modified a little bit because the lever itself has some mass, and you're going to move that in both experiments. But the idea is that everything moves the same in both experiments theoretically. So the motion of the lever on this side, the spring, the motion of the lever, everything will be exactly the same, and the only thing that'll be different is when you have the 2 mass on here, you're going to get 1 velocity, and when you have the 1 mass over here, you're going to get 2 velocity. And I don't think there's any way to make an argument to me that that somehow won't happen. That if you do it, you also have to put little stops on here so nothing can slide. You don't want the object to move this way as the lever's swinging. You don't want, this is going to be some centrifugal effect, right? It's not a force, it's the effect. There's going to be a little bit of force wasted in that direction, and you have to compensate for that and force it to go this way instead of that way. So obviously the faster object, that's more of a likelihood. This object's going to swing a larger distance, twice the distance that this one's going to swing. But, you know, it fixes the problem because this way you're using exactly the same amount of force from the spring. So even if you're not getting all of the energy from the spring, you're getting exactly the same amount of energy from the spring because the spring is feeling exactly the same resistive force. So the force here will be the same in both experiments. It will weigh the same, so to speak. You're pushing two things. This is done horizontally. Now, it could be done in gravity, but that sort of just makes a mess out of everything, complicates it. So this obviously done horizontally, okay, solves that problem. And all you have to do is make sure this surface is very slick, like glass or something. That's what the Brozo used, was glass, which was a good idea. And so this experiment will create a nice, clean experiment where you don't have to worry about whether or not you're getting the same amount of energy out of your explosive, so to speak, based on the fact that you don't have a, you know, the mechanism you're using isn't dynamite. It can't move at, you know, tremendous speeds. The pressure isn't instantaneous. It takes time for it to create the accelerations, all of those factors. And it just eliminates all of those, and it makes a nice, clean experiment where there really just can't be any reasonable debate. Now, their theory is that somehow this cannot travel at twice the velocity, that all it can do is 1.4, because that would conserve kinetic energy. And I'm saying quite obviously that yes, it will go twice the velocity. Now obviously you could modify this, and instead of the rubber band you could create a force like a pendulum or something here where you swung a two mass into the same distance. So I guess I can't really erase here. So I mean, you take a two mass and you swing it into the lever at the appropriate location for a two mass on the other side, and you see that see how much you can conserve, right? So you can swing one in this way and have the other one pop out that way, and figure out how much conservation there is in the lever system. Because again, you're going to move the lever, so you're going to definitely lose some energy to that friction, you know, that waste, that uncollectible energy of the motion of the lever. But again, the motion will be exactly the same motion whether the two mass is on here or whether the one mass is on here. And it's going to be the same weight, the same force, the same pressure. This will decelerate, okay, at exactly the same rate whether the one mass is out here or the two mass is here, because they weigh the same. At this point they create the same force. There won't be any difference between the force created here and the force created by the two mass at this location, because it's 1/2 the velocity here of here. So it's, again, you know, it's just too bad there's nobody out of all these people that have cranked and do all this cheap shotting and all this garbage about how I don't know what I'm talking. How come nobody can sit there and draw that and explain to me why it has to be this, and why they think that's realistic, that all I'm going to get is a 0.4 increase in the velocity, not a doubling of the velocity, just a 0.4 increase, that the whole thing will fail, that this lever will not move the same speed, that somehow the same exact weight will not be able to be pushed, that somehow the light thing has more inertia. I mean, none of it makes any sense. So anyway, I did do this experiment on my porch, and unfortunately I just didn't, you know, it wasn't good enough. It looked pretty good to me. I did a video showing it a couple weeks ago. You know, it seemed pretty dramatic. It seemed a lot more than 0.4 anyway. Okay, yeah, you know, maybe it wasn't twice the velocity, but it was a lot more than 0.4 faster. Brozo's experiment was, you know, 19 and 11 in terms of frame rate. So, the slow object went 11 frames, the fast object went 19 frames, Clearly, within the margins of error, that could have easily been 10 to 20, could have easily been understood. It's clearly far enough away from 1.4 to say, which one is it closer to? Well, it's damn shot a lot closer to 2 to 1 than it is 2 to 1.4. All right. So that's probably, I've done this before, but I'm just saying, the counter argument is just crap. Okay, nobody can do this. Nobody can just draw this and explain how the weight is different somehow. Somehow if I had a force detector over here, I could feel the difference between the two mass and the one mass. That if I pull on this thing and move those two objects, one of them at twice the speed, that somehow the force detector would feel a different force. And you've got to know it can't happen. Because it's exactly the same motion for both motions. It's exactly the same. How can the same motion, the same exact motion, be a different amount of force? So, too ridiculous. And, I can just do my part, and obviously you people just don't want to play along. You don't want to have a fair argument about your theory and its credibility. You just want to throw insults and defend crappy experiments. So, speaking of crappy experiments, let's go to this another thing I just noticed about the stupid Veritasium thing. I just thought I would throw it in because, it might be a piece of glaring evidence. Who knows? But it's just such a crappy experiment for such a bold claim. They're claiming that, you shoot a flashlight, and these photons, somehow there's photons that are, every photon that goes this way, it could have gone this way. All right. But it didn't like it. It sampled this way, and it said this way wasn't cool or fun. And so it decided to go this way. It's decided to land over here instead. Every one of these photons my hand is catching, you see. But it's very bright, right? So you could sort of understand that I could reflect the light off of here and have it go somewhere else, pretty easily. It's pretty bright. Yeah. Let's see, do I have something I could shine this on where you could see, when you have it the right focal length, you can actually see the LEDs, You can't really see that because it's just too bright. I don't know if you can see it there. Maybe. I don't know. I need a longer distance to shoot it, I think. But anyway. It's just so preposterous. You really think that the photons, the energy, the energy quanta, really do somehow sample the entire universe and then decide to go in one place instead. Instead of all the other places, it samples and says, this is more probable, therefore I'll go here. And that somehow I could do some chicanery over here, and all of a sudden I can make all the photons decide to go over here because somehow it's a better probability now. I've improved the probability because I put some stripes on it, and therefore the probability is improved. And so now that we'll see the photons that went sideways out of the flashlight. Come on, you can't believe this shit. Oh, God. But you do, it's just so depressing. Everybody is so fucking dumb. Damn it. You just have to be dumb to fall for this crap. You don't, these extraordinary claims, and you just don't care. They can give you any kind of crappy evidence, and you'll say, okay. Just so depressing. Video is playing again, I think. Anyway, shit, I was so screwed up something. So here he's done this silly experiment. He's showing how, so the laser beam is shooting a light, and he's claiming he's capturing the photons that were insanely improbable. The ones that bounce down and go this way. Okay, so they don't obey the equal and opposite angle rules, none of that stuff. Okay. They do something completely not seen by a real photon ever thing. So these are the 1 in a trillion kind of photons. He somehow is collecting them.
It appears.
And then he's saying, well, because I can see the light when I have this diffuser, it's a diffuser essentially, yeah, of course you can see it because it's reflecting. You can always see something better on a piece of paper than you can a mirror, because the mirror has these strict rules about where the light can go, where the paper doesn't. Anyway, it's going to scatter it in all directions.
So that shows really that we cannot get rid of the area which gives zero, that it really is canceling out.
So there's this area that is zero. This is all these insanely insane possibilities, like a photon comes out of my flashlight and goes to Saturn. They're saying that all those things really do happen. Okay, it really is. The radar goes there and says, no, we don't want to go there for some reason because it's improbable. So it doesn't make any. I wish I could explain it, but I can't even explain it coherently because it doesn't make any sense at all.
If we do clever things to it, we can demonstrate the reality of the reflections from this part of the mirror.
Right, so they can't do any of that. All right, so this is the only part I wanted this for. Maybe I can make this bigger, because it is curious that, all right, so, they have all these images. All this stuff is so difficult. He's got a little inset here. That's the flat part. Okay, and then they're showing you this is where the card is, and this is the actual place where he's holding the laser is here. All right, so let's zoom into that, because, I just noticed that ain't right either. So there's a light bulb still there, okay, but he's not got it on. So he's holding a laser and shooting it down towards this paper, right? Let's use this again. Nope, that's the wrong thing. Can't do that. I want this thing. All right, so here's the spot where he's shooting the laser down on the card. But why are there all these other lights here? What's all this stuff? There's a little dot here, a little dot here. What is that? And so the light bulb is still there, right? The reflector for the light bulb. So you gotta understand, there's a reflector in a light bulb. And that's still there. So does that entirely make sense to you? So let's just play a little more of this and see if that changes. Now I'll get the arrow the hell out of the way. Let's see if that changes. That moves off the screen, which is sort of irritating. Let's see, I gotta find that. Nope, that ain't it. That might be it, yeah. Okay, I'll move it all the way over. Okay, so that wasn't very helpful. All right, but you get the idea that what were all those little lights? So it just seems strange. The laser beam should just be one spot, you see. You shouldn't be seeing three different kinds of little blobs of light. It's a laser beam. There shouldn't be any other light visible. So I am saying that what you're seeing is part of the reflection. The spot is going back up into the reflector of the light and bouncing around in there, and that's what you're seeing. All right, so I need to get the hell out of this thing. Yeah, that sort of worked. Okay, I can move this. Whoops, I can move something. This is always in the way. I gotta get rid of the arrow. All right, so maybe I'll just call that a video. That's enough, I think. Just, it is frustrating to have this conversation about the fact that, experiments do have to be made credible. You can't have wrong assumptions in the experiment. And then you have, data that's of no value. And all these variables are really important, and nobody takes any of them seriously. And it really does suck. All right, so till the next time and such and so forth and whatnot. Christ. Yeah, that's enough.